Welcome. Let's take a look at number 7. In order to qualify for a police academy, applicants are given a test of physical fitness. The scores are normally distributed with a mean of 64 and a standard deviation of 12. And we're going to be looking for the cutoff score on the fitness test that would place an applicant in the top 20%. All right, I'm going to identify the given information. So we have our population mean 64. We have our population standard deviation 12. And we're trying to find the cutoff score. So we're going to use our random variable x for a data value, a cutoff score in this case, a score. And they wanted to separate the top 20% from the rest. So top 20 would be identifying the area to the right of the x value that we're trying to find. And I'll just go ahead and put that in decimal. So we know to find data values, we inverse norm the area left of the data value, and then we include the mu and sigma. So right now I know the area right of the data value. So let's go ahead and find the area to the left of it. So the area to the left of it minus area to the right. And that's going to be 0.80. Now we can inverse norm. So inverse norm that area to the left. So don't inverse norm the 20% because that's the right area. So now we've got the left area, and then we put in our mu and our sigma. And you're welcome to check that out. I'm going to round to a whole number, and that would be a score of 74. So the average was 64, but if you want to be in the top 20%, you're going to need a score higher than that. You'll need a 74. All right, let's see how that's different than number 8. So the amount of money spent on food each month by a single adult living in an area of Los Angeles is normally distributed with a mean of 370, a standard deviation of 45. And it again says find a cutoff. So in this case, a cutoff amount. So now we're finding that random variable that puts a single adult in the bottom 10%. All right, so our given information now, we have our mean, 370. We have our population standard deviation, 45. And now they gave us the bottom percent that they desire. So that's the area left of the value we're looking for. So area left is 10%. So if we're looking for data value, we always inverse norm the area left, and they gave us the area left. So we put in our area left, we put in our mu, and we put in our sigma. And I'm going to round to a whole number again. I'll put units here, so that would come out to be $312. You can check that out on your calculator, make sure you're good. All right, so we really want to see the difference between those two problems. So if they give us the top area to the right, we find the area left and inverse norm. If they give you the bottom area is the inverse left. I'm sorry, is the area left. So we can go straight to inverse norm. All right, so we just make sure we're always doing inverse norm, the area to the left. All right, let's move on here, number 9. So according to Boeing data, the 757 airliner carries 200 passengers and it has an entry door height of 72 inches. We'll assume men's heights are normally distributed with a mean of 69 inches. I'm just going to document that down here. So for this population of men, the mean is 69.0 inches. and the standard deviation is 2.8 inches, we'd like to know the probability a man will have to bend in order to pass through the entry door of the 757 airline. All right, so men's heights are normally distributed. We have our bell curve. So my x-axis over there in inches, and the average is 69 for this population. And again, we could include more information on the x-axis, but we're not trying to draw these perfectly to scale. So I'm just going to be including the mean. And if they're going to bend to pass through the door, that would be men that are taller than the door. And the door is 72 inches. So I'll just put that somewhere to the right of center. So there's the door. So men taller than the door would have to bend to get through. All right, so the question is, what is the probability that X, the height of a man, is greater than the door of 72 inches? All right, so if we're looking for probability or area, and we're in the greater than case, we're shading to the right, then our lower bound is our value 72, and in theory, we shade forever. So that concept of infinity as our upper bound. And then on the calculators, so in the CDF, we're finding area or probability. And we start with our lower bound, 72, and then 90, E99 for our infinity. And then we need to include the mean and the standard deviation. All right, you can check that one out. I'm going to round that to 4 places. That will be 0.1420. And I'll write that in percent here as we complete the sentence. So I can now tell you that with a door height of 72 inches, there is a 14.20% chance a man entering the aircraft will have to bend to pass through that door. All right, let's move on to number 10. So a particular new car has a mean gas mileage of 341 miles per gallon, a standard deviation of 5.1 miles per gallon. We'll assume mileages are normally distributed, and X will represent the mileage for one of these cars. All right, so for A, we're wanting to find the probability that a car has a gas mileage between 30 and 40 miles per gallon. Okay, so I'm going to rewrite the question here just for emphasis, but the variable is X. So X is mileage of a single car picked at random. So the chances that the car has a mileage between two numbers, so probability is mu CDF, lower limit, upper limit, and then mu and zero. And that will come out to be 0.6656. And just for practice, I'll keep writing it as percent as well. So decimal or percent. And I would let you know which one I would like if you asked. All right, and then we have a probability that a car has a gas mileage less than 32 miles per gallon. So again, I'm just going to rewrite that question to remind you, X is for the mileage of a singular car. So X less than 32. And when we're doing the less than case on a graph, that would be shading to the left. We start at our negative infinity as our lower bound, and then our upper bound is the value. And then again, mu and sigma. Yeah, that one will be 3403. or 34.03% if you would like to check that one out. All right, now on part C, it says a company purchases a random sample of 12 cars. So before we had a singular car that we were interested in, and now we're going to be looking for probability concerning a sample of cars. So the question is, find the probability that the sample mean, so X bar, the mean of the 12 cars, is less than 32 miles per gallon. So what we have to pay attention to here is that when we're given a sample, 12 cars, and we're looking for probabilities concerning the mean of the sample, we use the central limit theorem. So our central limit theorem would tell us that the mean, population mean of the sampling distribution X bar, so the distribution of the samples, that mean remains the mean of the original population. So our mean remains the same, 34.1, but the standard deviation of the sampling distribution changes based on the formula sigma over the square root of n. So we take our original sigma, 5.1, and we need to divide that by the square root of 12. So that is the change you really need to pay attention to. So our sigma changes because it's a sample of cars, and our probability will not have an X in it, that's an individual car. Our probability has X bar. And again, just rewriting that for emphasis, so now it's the probability the sample mean is less than 32. So the order remains the same. We're still shading to the left, the less than case. Start at negative infinity. And then the upper limit, 32. And 34.1, the mean stays the same as the original population, but when we get to standard deviation, we do 5.1 divided by the square root of 12. So that part is very important, and make sure that when you enter it on a calculator, you hit divide there. Sometimes students leave that out accidentally, and then check that out. That should be 0.0769 or 7.69%. Okay, and that ends that page.